Hello, good afternoon, everybody. We continue our experiments with a super duper blackboard. So again, please be indulgent. I'm trying it on this big screen for the first time, and you see I have electronic digital chalk. So with a normal piece of chalk, you cannot do it like this. So this is yet another advantage. And as announced, today I'm going to lecture just for 15 minutes, and then I will pass the floor to Paul Baum. But I want to show you one more lemma, which will be proven in the recitation class in this afternoon, which concerns factoriality of the extended graph construction. But before I can make sense out of this lemma, I have to recall the basic definitions from the previous semester. Of course, you already know what the homomorphism of graphs is, so I'm not going to do it. But what do we mean by a proper homomorphism of graphs? Well, a proper map between topological spaces is a map with a property that the preimage of a compact set is compact. I mean, that's in the category, say, of locally compact Hausdorff spaces. If you go to abstract topology and you look at Bourbaki, it's far more complicated, but we don't need it. And in the discrete topology, proper maps are simply finite to one maps, okay? Because every compact set in discrete topology is finite. And of course, as always, we must respect the endpoint and the beginning points of our edges. And here, this finite to one simply means that when I have a preimage of any vertex under F0 and preimage of any edge under F1, then the set which I obtain is finite. So this is proper homomorphism of graphs. And now the very important part, which I want to show you, and now I have to minimize. You see, it's not so easy because I'm seeing you, and when I see you, I don't see my controls. Now I have a pen. Yes, now I can write. So you see, this is a very, very important thing, which I'm recalling for you right now, so that you know what I mean by a path homomorphism of graphs. Okay, so I have my graphs E and F. This allows me to construct the set of finite paths in respective graphs. And by a path homomorphism of graphs, I mean a set theoretical map from finite paths in E to finite paths in F, satisfying some more or less obvious conditions. So first, you map vertices to vertices. Secondly, as it was before, you respect the endpoints and the beginning, starting points and endpoints of your paths. Okay, so this is what is point number 2 in this commutation relation. And then finally, you have this kind of homomorphism-like property. If you concatenate two paths, P and Q, then f of PQ is just concatenation of f of P and f of Q. And of course, we can concatenate because, as I told you, this f respects the endpoints and the start points of the graphs. Okay, so this is a very important concept which I'm going to use in this lemma of today. And now, as you can guess, a proper path homomorphism is a path homomorphism which is finite to one, which is written right here. And then we have lots and lots of additional properties, but I want you really to bear in mind these three, because they, no matter what kind of category graphs you study, these three properties are the basic minimums that you have to satisfy. I mean, you don't have a category of graphs without these three properties satisfied. And now we do some fine tuning, that is, we add some further conditions, all right? So now I can stop sharing this screen. I can now start sharing the whiteboard, and the rest I can just write. Okay. There are too many controls here, so it's not so easy to do it. So that's the advantage of having two screens. When you can have some stuff on one screen, some stuff on another. Now I can fold my digital chalk and start today's lecture. So this will be in the form of a lemma. And we take any path homomorphism of graphs. So let F E F be any path homomorphism of graphs. So here I mean an arrow in the category, right? Technically speaking, this is a map from FPE to FPF when we look at it in the set theoretical manner. Okay, then the formulas that I'm going to spell out for you will define a homomorphism of extended graphs. Okay, so what are the formulas? So first, I'm saying that on edges, nothing happens. Okay, maybe I should have mentioned it more clearly. So just as before, we were showing the factoriality of the EX construction. Here we show the factoriality of extended graph constructions, because at the end of the day, when we want to pass the factoriality of relative Kunz path algebras and Levy path algebras and graph sister algebras, well, it goes with the extended graph construction. So let's see first how factorial this is. And this is actually perfectly factorial, as you will see in this lemma. Okay, so first, for any vertex, because you see now I have an F between E and F, and I want to construct F bar, which goes from E bar to F bar. All right. So I'm going just to give some assignments, and then it will have to be verified that it holds water, makes sense, is well defined, and really it defines a functor. Okay, so first on edges nothing happens, because remember the edges of a graph are the same as the edges of the extended graph. So this is very easy. F bar of V is by definition just F of V. And now when you look into edges, well, it's almost the same. So you take any edge in E1. So what happens? Well, F bar of E is nothing but F of E. But as you can expect, F bar of E star, of the ghost edge, that's by definition F applied to E, and then the ghost edge related to this. Okay, so I sort of designed it to be a star homomorphism in the future once you get to sister algebras. And now how do we do it for paths, which are length bigger than 1? So for convenience, let me take any path which is already in the extended graph. Okay, so I have a finite sequence of edges in E bar, so x1 dot 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 xn. And I say that this is a finite path in E bar, because you know what I do, what I assign to edges that are both starred and unstarred. So now I can easily define it as follows, that F bar of such a path is nothing but, you can guess, F bar applies to x1, dot dot dot, F bar applies to xn. And of course, you have to check that, for instance, this is a path. That's what we want. All right. So the claim of the lemma is that the formulas define a path homomorphism F bar from E bar to F bar of the extended graphs. And moreover, they do it in such a way that the assignment E going to E bar, F going to F bar, defines an endofunctor defines a covariant endofunctor. Where are my controls now to have an eraser? Okay. Covariant endofunctor of the category of graphs and path homomorphisms. Okay, so this is the first part of the lemma. It's not a big deal, but Niklas will carefully check all the properties. We have to check it to make sure that there is no error anywhere. So at this sort of eminent level, we take this biggest possible category. See, when I speak about categories of graphs, I always have the same class of objects. My objects are graphs, that's it, right? But now I'm restricting to more and more specific morphisms. I demand more and more of them. And then I want to make sure that when I have restrictions in the domain of my covariant functor, they are satisfied in the codomain. So it preserves it. So it defines, it restricts to end of functors of subcategories. So that's the first part. And now I can go to the next page. It's one of my most beloved features that I can do without erasing to the next part. So the second part of the lemma says that, as I just announced, this end of functor restricts to end of functors, of course, covariant ones, of the following subcategories of graphs. Now it's going to be a very long list, but we will need it. And maybe even we will need something more, but I couldn't think of it at this time. So first, PTG. So proper path homomorphisms. So morphisms are proper path homomorphisms. So what I add as a requirement is properness. In other words, if I have a proper morphism between graphs, then the induced morphism between the extended graphs is also proper. Okay. So that is a quick checking which Niklas will go. Now, OG. So this is this category of graph homomorphisms. Okay. So morphisms are graph homomorphisms. So this means that not only I map vertices to vertices, but also I map edges to edges. So if you want, these are path homomorphisms that preserve the length. And now you can intersect these two categories and have POG. So morphisms are, so here it's graph, which is important. Here morphisms are proper graph homomorphisms. So of course, when you prove 1 and 2, 3 follows, right? Because this is like the intersection of these two subcategories is the third subcategory. Don't worry, I have only 1, 2, 3, 4 left. And then the floor goes to Paul Bauer. Okay, IPG. So by the way, so these properties of properness, they're important when you want to have a contravariant functor from the category of graphs with whatever morphisms to the category of path algebras, or Levi path algebras, or Kohn path algebras, or graph sister algebras. So when you construct the contravariant functor, you must have this properness, otherwise it doesn't work. Now, if you are constructed in a covariant manner, then what you want is to have some injectivity properties. Otherwise, these consquilant relations will be violated. Okay, so IPG. So here, morphisms are path homomorphisms vertices. More precisely, what I'm saying is that I have a path homomorphism of graphs, which means a set theoretical map from FPE to FPF. And now when I restrict it to paths of length 0, I'm injective. Of course, I'm at paths of length 0 to paths of length 0 as one is the first axiom, but I demand this map to be injective. Okay, so this is I for injective path homomorphisms. Now, BPG, I simply switch injective to bijective. This is to preserve unitality in case your set of vertices is finite. So bijective. On vertices. Okay, I'm afraid I'll have to go to the next page because I still have 2 more to write down. And these will be actually needed in our compact algebraic lemma. So this I call IIPG. Unfortunately, I have to write it anew. So morphisms are path homomorphisms. That are injective on vertices and edges. Okay, and here you can ask yourself the following question. If I'm injective on vertices and edges, must I be injective globally on all paths? No. No. And this is a beautiful example. I already told you about it a week ago. If this is my graph E, so with just one edge, one vertex, and this is my graph F with just one vertex, okay? Then nothing can stop me by sending everything to this vertex. And I'm injective on edges because I have only one edge. But I'm by no means injective on paths because all paths are mapped into one path. So I'm shrinking it into 1 point. I mean, this is a 1-point set. So FPF is just 1-point set. Okay, so of course I'm not injective. But I'm injective on vertices and I'm injective on edges. So for having functoriality for absolute compact algebras, it works. And in fact, I was telling you that this is the Tepley's algebra, and this is first the symbol map into the circle algebra, and then evaluation at 1. So this is a perfectly legit graph homomorphism of graph system algebra. Now raise. I remember in Germany you would have this bucket of water and you would soak the sponge in bucket of water. Then you'd have this like wipers in the car to clean it. It's so much easier now. Okay, go back to drawing. And then we have IBPG. Well, so the beginning is the same, the first line is identical. But I, not quite, sorry, not quite. That are bijective on vertices, again, just to preserve unitarity. Bijective on vertices and injective on edges. And that's it. This is, and again, this is even more than I wanted. It's 20 minutes, 19. So that's all I wanted to tell you today. And then now I pass the floor to Paul Baum. Please tell me if you have any questions. So this lemma is going to be proven today by Niklas in the recitation class. And prior to this, the proposition about the functoriality of the EFF construction is going to be proved by Michał. So if you don't have any questions, I'll stop recording and we start Paul Baum. Any questions? Zoom folks? Okay, so I now stop recording because program is already recorded. And you have to give me a second to start video from the Banach Center.